Alright, this is Crash Course on DE. It's the first 5 worksheets, so it's going to be a long video. Alright, so the first question, determine whether the given function is a solution to the corresponding differential equation. So here's our differential equation right here. Y equals 2e to the x plus 3e to the 2x. And then y double prime minus 3y prime plus 2y equals 0. So this one's pretty straightforward. You just got to take this equation, differentiate it once and twice, and then plug it into this guy. So then so we've got a single y double prime, so that's this guy, minus 3y prime, which is this guy, and plus 2y equals 0. And then we'll find that these all cancel out and 0 equals 0, so this one is a solution. So this one here, we got to take a look at this equation. It's the same, determine whether the given function is a solution, so this is continuing on from this. So we're going to use implicit differentiation with this one because I don't want to take y as a cube root of all that other bullshit divided, multiplied and added and all that crap. So this will be easier if we just do it implicitly. So we can go ahead and differentiate this thing. So we've got 2x, because that's the derivative of x squared, plus 3y squared dy dx, minus sine xy times the shit inside, which is x dy dx, because we took that with respect to y, plus y equals 0. So, and then what we're going to do is we're going to see this equals that. We can rearrange this all and get the same thing we had here, so that works. Alright, this one. So this is where we actually start doing some differential equations and solving them. So this first guy constitutes a separable equation because we can separate what we've got, just y's in the numerator and x's in the denominator. So this is the general thing that you should have memorized for the formula sheet. Dy dx equals p of y times g of x. It's going to be this solution. So you want to separate these guys if you can, and then integrate both sides. So this one is tan inverse. This one is y over that. This one's tan inverse. This guy here, we got to do a u substitution. So we get this, but we don't have a 2, so then we got to multiply by 1/2. So that's going to be 1/2 ln of u, which u is 1 plus y squared, and then this one's tan inverse of x. And don't forget your plus c's. So that's it. This one is separable also. You take x sine x, and then the dx can come up here, and then we gotta integrate this way. So I just did them separately, so that's this one. That's easy enough. And then this one we're gonna do by parts, so I've got a u equals x, du equals dx, dv is sine x dx, so you integrate that and you're going to get minus cosine x. So then you go ahead and set that equal to that, and then compute this integral, and then you're going to get this, this one equals this one, and then we just solve for y, and then we're going to get that. So this one here is a first order linear. So this one, a first order linear is in this form: y prime, which is this, p of x times y, so p of x would be 1 over x, equals q of x. So there's just x's over here. So again, I just rewrote it like this to match that a little bit. So these ones, the trick to it is you got to get an integrating factor. The integrating factor, which is mu, mu is going to be e raised to the integral of this p of x function, which is 1 over x. So, and it's good when you get something like that, because when you integrate 1 over x, you get ln x. E to the ln x is just going to be x. So y is going to be 1 over, the formula is 1 over mu times the integral of mu x times q of x dx, which is, this is q of x in this case. And then put a plus c there, even though you're doing it beforehand, just so you don't forget to distribute this, because c is going to be multiplied by this shit. So anyway, to compute this integral, we're going to have to do another by parts integration. So that's easy enough. That's 1 over mu. Again, mu is just x times q of x, which is this guy, plus c. So u, v, etc. So this is uv minus the integral of v to u. And then I had to do it again. Or sorry, I had to do a... Yeah, I did a u sub just to make this easier. So we got this, and then we go ahead and distribute that x, and then we're going to get that as our solution. Okay, what's this one? Well, notice we've got a function of x multiplying here, so we're going to divide by this. Look, and that's okay because x is greater than minus 1 in this case. So this thing's never going to hit 0, so everything's kosher. So anyway, we're going to go and do this, and then we'll get our integrating factor. So we take this function here that's multiplying the y, that's p of x. So mu is going to be e raised to the integral of that shit. That's one that we had before, so this should be, yeah, ln u minus u because there's a negative sign. So it's going to be this, which is this. So mu is going to be e to the ln of that times e to the ln of that, or e to this, right? So you can split those up. So that's e to this plus e, or times e to that, and then we're going to get this guy. So 1 over mu is going to look like that, and then we just take mu, which is this, multiply it by our q of x, which is this one. And then we're going to get, let's see. Okay, so we had that factor of x plus 1, and that disappears. We can then factor out an x, or no, I guess we're not going to factor out an x. I did another by parts. So now we get this one. Right, I did this one by, oh, right, so that's uv, v to u. So I said u is this, so yeah, v du is going to be this. So I'm just rewriting this integral equals this shit. And damn, yeah, this one took a while. So yeah, so just put a negative sign out in front of that because it's e to the whatever. I should have a bracket here. Let's put that there. Oh god, yeah. The last thing I wrote was like the Metro version has this like weird galaxy color thing, so I just put that wherever I really need to pay attention. We're only 7 minutes in. All right, cool. So anyway, we're gonna go with this, and then this guy is another integral, and to compute that integral, I'm gonna do another by parts, and then it's gonna be this shit, and eventually this is all there. Now I can fucking integrate it. Okay, so then we got this, all this shit, and we're gonna multiply it by 1 over mu. So I wanted to factor out this so then I can cancel those e's out, and so that's what we're left with, this ugly looking thing. All right, so that's our general solution. Find the solution to the initial value problem. Okay, cool enough. I have 2 equals 0. So I guess because we're using this, it's okay to divide by x. It didn't say that it's in a range, but I guess it's kosher because we're evaluating at 2, so we're not actually dividing by 0 at this point. So I think that's okay. dy dx is this. This one is separable by the looks of it, right? Because we've got well, we can separate it. So there we go. So there's e to the y. So that's the easiest integral in the world to do. And then we can separate this out, so that's going to be 1 plus 1 over x, so that's also very easy. So we just integrate 1, that gives us x, and we integrate 1 over x, and that gives us ln x plus c. So this is implicit. Okay, so now we're going to plug in y of 2. So again, y was, well, y of 2 so is going to be 0, so this y is going to be 0. And then we're plugging in 2 everywhere we see an x. So that's going to be what c is. So now we can actually just put it all in here. And if we want, we'll just take ln of both sides and get y in terms of this ugliness. So anyway, that's cool. So this one here, this one's done by substitution. So the substitution, I guess I don't have the recipe for that. But anyway, it's basically whatever your substitution is, you're going to say u is this shit. this is the substitution we want to make. There's basically 2 that we've done, so I can't imagine that we're going to see a whole bunch of them. But so this is y over x, so I'm going to rearrange this to get it in terms of y, because what we want is we just want to swap this dy dx out, because when we do that, then we can turn this thing into a separable equation, and then we can, you know, employ our regular separable techniques to this. So we get u plus this shit, because this is implicitly done, right? So this is first times derivative of the second plus second times the derivative of the first. So first times derivative of the second, so that'd be u times the derivative of x is 1 plus x times du dx. And that's equal to dy dx. So now we've got a dy dx, so we're just going to sub that in. So that's going to be u plus x du dx, and that's going to be this one. And that's equal to, and remember we said u is y over x, so we get that. So now we can get those u's to cancel. And look at that. Now we've got something we can separate, right? Because anywhere we saw a y, we're just going to make this substitution here. And when you factor out an x squared, you're going to get that. So now we can take that x squared and multiply that over here. Right. Okay, so then, yeah, anyway, this is separable. So we're going to take this dx and move it over here. And this x is going to come down here, and this is going to come up here. And then we go ahead and integrate that. So that's u, and u cubed over 3. And then this is x to the minus 3. So when we integrate that, it's to the minus 2. So the minus 2... that's right? Oh yeah, because we're dividing by it. Sorry, I've been taking a lot of derivatives today. Anyway, okay, so there we go. And then now we can sub back in what we had before for in terms of y and x. So then we get this implicit solution. So that's how you do a substitution. This one is the exact same substitution. Basically, if you see this, that should be a red flag. All right, so anyway, we're going to go and do this, and then now we do our implicit differentiation. This is the exact same thing we did before. Cancel out the u's, and now we can factor out an x and get that to cancel. Now we've got ourselves a separable thing that we can then integrate. So this is, took this fraction, split it up as usual. So this is going to be, that's going to be ln of x. This one's going to be, must have had to do, yeah, I did a u substitution here. So 1 plus u is z, dz, du. So I did it for this one here. That's going to be this. And then I split that up again and got this. So ln of 1 plus u, right, so that was a u sub. Ln of 1 plus u is this one, minus 1 plus u, right, that because that's minus z, which I said was 1 plus u, plus ln of z, which is ln of 1 plus u, equals ln of x plus c. And then I had 2 of these, so it's 2 ln 1 plus u minus 1 plus u. And we just, wherever we see a u, just plug in our y over x there, and then we're good. Okay, what were we at? 13 minutes. Okay, so dy dx. This one is a different kind of substitution. So u, we're going to say, is x minus y. Do our differentiation, set it equal to dy. Take that, whatever you got here, and plug it in. So 1 minus du dx equals sine of u, because x minus y is u. So we got du dx, now we've got this. So this one's separable, then this is just dx. So then we're going to get, now we're going to take this apart and just take a closer look at it. This is going to be 1 plus sine u on the bottom. I must have, yes, I multiplied by the conjugate and got this out here, so I have that, and then I use the trig identity there to turn that into a cosine u, just because I could split up this fraction, so it's 1 over this shit, so that's 1 over cosine u, that's secant. Why did I say it was secant squared? What? Oh, because I didn't have a, yeah. Okay, there we go. Dum dum. All right, so there we go. So then we have this, and this is that shit. So we can, this one we can do like a, well, I've used u as a substitution already, so I'm going to use another one called z. So I said z is cosine u, so that's 1 over z squared, and then this shit, and that negative disappeared. We get that. So everybody knows this one. That one's great. That's well behaved. And then this is 1 over cosine u, which is secant. And then so tan u plus secant u equals x plus c. And that's our solution, or implicit solution for that. Okay, so this one screams exact because we have a function here and a function here. You know, maybe not exact, but it's good to check it. I mean, this looks tasty, right? Look, we see the derivative sitting in here. We got a tan over here. And then these are just like swapping powers around. It looks like it could be worth it. So here's the skinny on exact. Exact. M of x of y dx plus n of x and y dy equals 0. And it's exact if you take the partial with respect to y of m. Because, look, this is dx, right? So if you do dy, this is... what is it called? Like Clairaut's theorem or something like that. You take the partial derivatives in alternating order and of any equation, it's going to be the same thing. So anyway, when these are exact, this will equal that. And then basically what you're going to do is you're going to say my main function, the original function, if I took the derivative with respect to x, I'm going to get m. Or if I take the derivative with respect to y, I'm going to get n, right? So then what I can do is exploit this exact thing. Now this particular one is exact, I know that already. So anyway, let's say this is m, this is n. M is the one that's multiplying dx, n is the dy, if you want to keep the terminology straight. Alright, so my, let's do that. So that 2 comes down, multiplies the 6, and this is secant squared y, because that's just a function of y, and lo and behold, they're the same thing. So therefore they're exact. So f, I said, is if I integrate m, because m is basically like that function with the partial derivative done to it with respect to x already. So if I integrate that, I'm going to get this shit. Well, anyway, I just subbed in m, so then I integrated it. So this is going to be done with respect to x. So this is x cubed over 3. Well, that 3 disappears. And then this tan y just gets an x because it's treated like a constant, plus some function of y. We don't know what it is. So now we're going to take this f and we're going to differentiate it with respect to y, which should give us n, right? So if we do that with respect to y, we're going to get this 2x cubed y plus x secant squared y, right? Because this is just the function of y, so that x comes along for the ride. And plus g prime of y. Now I'm looking at n, I'm comparing it to n. Well, it turns out g prime of y is 0, so that means g was just a scalar, right? So then, I mean, you could write f here, but I've been writing f, but then I noticed in the solutions it's k, so maybe I'll just say k is that, because f is kind of this like placeholder, because you're not quite sure what's going on at that time. Anyway, so that's cool. Let's do this one. So this times dy, dx times this. I bring those both back up. So I've got my n, because that's the dy one, and then my m, that's the dx one. So take n with respect to x, m with respect to y. Turns out they're the same thing, so they're exact. So let's do the exact same thing. Let's integrate m with respect to x. We can get this, because m was this. So when we integrate that with respect to x, right, because we take the derivative of this, we're going to get that. And then 1 over y with respect to x, you're just going to multiply that by x plus this, remember that function of g of y. So then take f with respect to y, you're going to get this shit. Compare that to n, and it turns out the g prime of y is 0 again, so we get that. So this is the initial value problem version of this guy. So take the two partials with respect to the other, whatever is the opposite of this. And we're going to find out that these aren't exact. So now we can use an integrating factor with these ones. And so all we have to do is, the integrating factor is going to be mu is e raised to the integral of this shit. So we have my, we have nx, right? And divided by n. So if the function is just of x, and then alternatively we can do nx minus my over m dy, and raise e to that integral if it's a function of y. So let's just calculate these and see what they are. So I take my minus nx, and I get this shit. Well, that's got x's and y's all over the place. I don't want to have to deal with that. So let's try this one. So again, nx, plug in the negative my over m, and ooh, look at that. That's pretty. So we got 1 over y. So let's go ahead and, now mu is with respect to y, right? Because this is y, so it's a function of y, so this is what we're going to calculate. So we're going to take that, it's 1 over y, and it's going to be, we're going to take the integral of that. Well, great, it's ln of y, so e to the ln of y is going to be y, right? So now, the key to this is, now that we got mu, we take mu in our original equation, and we multiply that shit out. So it's just y. So we're going to have an extra y. This y is going to get distributed on both of these. I don't know why it does this. It's like, I have to like squiggle and then erase it. Anyway. Okay, so now we've got m and n. So f is going to be the integral of that. Right? Like, we could do the partials again and find out that they're exact now, but that was the whole point of doing the mu thing. So I'm not going to do it again, obviously. So let's take m and integrate it with respect to x. Is that what I've been? Yeah, okay. We integrate it with respect to x and get this. Or sorry, that's m, and then we integrate it with respect to x. So x raises a power, that 3 drops out. X raises a power, that 2 drops out. Plus g of y. Take f with respect to y. So then that 2 comes down and that 3 comes down. And we get g prime of y. Compare that shit to that. So look, turns out g prime of y is y. So if we integrate that, then we're going to get y squared over 2. So k equals this shit. Right? Because this was 0. It should be this. Right? But I don't know. I left it like this. So we'll just solve for k. So solve for k after plugging in 1s where all the x's are, and anywhere you see a y, chuck a 2 in. And there we go. Beautiful. Alright, so let's keep going. So that was the only question we had on the whole thing like that. I kind of like those questions anyway. Alright, so find a complete solution for the Bernoulli equations. So here's the deal. This power has got to be bigger than, what was it? It can't be 0 or 1 or negative. It has to be greater. I think it has to be a squared term. If I need to look that up. But this is how you integrate it. So this is in that form, right? So p of x is x, q of x is x, and y to the n in this case is 5. So we're going to use a substitution where u equals y to the 1 minus n. So I do that here. U equals y to the minus 4, right? Because 1 minus 5 is negative 4. So then let's do some implicit differentiation here. We're going to get du dx is this shit. Rearrange that. So what you want is, when you divide by y to the 5, you're going to get this, right? You need it to be just a function of x over here. So now that we have this, we're trying to massage this to look like this side. So that's what I got to plug in to get it to look like that. So that's what I do. And remember, u is y to the minus 4. So anywhere I see y to the minus 4, I can plug that in. And then I'm going to divide by negative 1/4 to get negative 4 here and negative 4 here. Now it's in a form that we can deal with it, right? So now we're just going to use a regular integrating factor. So this would be p of x in this case. So now we've got mu is going to be e raised to the integral of this p of x function. So mu is going to be this. So now, because of that, u is going to be 1 over mu, right? Because this was negative. So 1 over mu. multiplied by the integral of mu times q of x, which is negative 4x. I had to do a double take there because p of x happens to be q of x in this case. Maybe in all cases for Bernoulli, I'm not sure. I couldn't tell you for sure, but that might just be how the math works out. So yeah, we get this. This is looks like a u sub. Oh right, yeah, because we got the derivative of that is just sitting right there, so we can go ahead and do that. Right, so yeah, so that 4x dx comes there, so that's e to the z, because I'm already using u, e to the z plus c. So we're going to distribute that, so we're going to get 1 because this cancels out perfectly, and then it's that, so u is that. Remember, u is y to the minus 4, so then we're going to invert that guy and then raise it to the 1/4 and solve for y. Alright, so there we go. This one is, well, what you want is you typically want to have this dy dx by itself out here if you can. So let's go ahead and multiply this. So I'm going to get 2y and then y squared here, right? So that's then again Bernoulli. So make the u sub, it's if n is 2 now, right? Because n is 2. It's when it's in this form, that's when you can apply Bernoulli. So you got to make sure it looks like that. So anyway, u equals y to the 1 minus n. So u is 1 over y. So then we do our implicit differentiation here. And what did we have when we divide by y squared? We get y to the minus 2 dy dx. So we need to have that here. So that's what we're going to replace that with. And then I'm going to multiply by minus 1, or divide by minus 1 to get it in this form. So now I got my p of x. So mu is going to be e raised to the p of x, integral of p of x, which is going to be 1 over x squared, because that negative 2 can come over here, and we get e to the ln of x to the minus 2, so u is going to be 1 over x squared. Okay, so then u, not mu, u is going to be 1 over mu, which is going to be x squared, times mu times, which is this shit, this shit right here. Because remember, it's not the original one, it's the linear one. So then that's going to be, yeah, q of x or whatever I called it. So x is, oh sorry, well that's on the bottom, so it's going to be minus 3x to the minus 3, so we're going to raise that up. That negative is going to cancel out, so we're going to get 3 halves x to the minus 2 plus c, and I'm going to distribute that x squared. So then that x squared is going to cancel this x to the minus 2 up top here. We're going to get cx squared, so u is this. Remember, u was 1 over y, so then we do 1 over y, take the inverse of this shit, and get that. Okay. I think that's enough for one video. I'll come back for another one.